All right, welcome to week 15. We're continuing our discussion of acceleration structures today. We're going to take a look at the quad tree code that the two students in this class wrote. And I think it might be beneficial if we just kind of look at what I pushed out. It's called quad tree map. Just copy this recursively to Okay, so if you recall last time, we get an infinite loop because it can't divide once when 2 points are next to each other, right? So, yeah, we went over some cool stuff. The spatial operator, little point class here, which probably add more stuff. Operator plus and minus, and make a little vector class, but it's not really our point for today.
Your stream stopped, by the way?
The stream stopped, by the way. Okay. So let's pull that back up. Here we go. Okay, so Stover, where did you get stuck on the assignment? Your insert. You said your insert wasn't working. Okay, let's take a look. Okay, so that looks like my code. My code. So what did you do? This looks pretty much like the same code that I have over here. This looks pretty much identical code. The leaf boolean, it switches back and forth between being a leaf and not a leaf, so I was looking for a solution. Okay. So, yeah, it's kind of a weird design that I came up with. Because when we start off, you shouldn't have any leaves that are not leaves or something. I don't know. Or like a leaf has a data in it or not. So, when we start our tree, it's going to have the range 0 to 100 in it. And it's not, I think it defaults to not a leaf. And then you put a point into it, now it is a leaf. And it copies the point in, it can hold a point, a quad tree can hold a point. And if it holds a point, then it doesn't, then all of its kids are null. All of the children are null. If its children are not null, then it doesn't have a point. Okay, so these are kind of mutually exclusive things here. If we really wanted to save some space, we could probably use a union or a variant to save a little bit of RAM, but I don't actually care that much about it. Okay, so yeah, so if we insert, right. The problem is, let's see here. So the first time you insert into it, it becomes a leaf. The second time, it becomes not a leaf. And then the third time, it becomes a leaf again. Right, so we can't do that. We have to say if it's not a leaf and all of our kids are null. Okay. And so, and not UL, and actually, that's good enough. So they all get created at the same time. So that, maybe you should fix it, flipping back and forth between true and false, because there's 3 states, right? It's empty, and it's got null kids. It's full, it's got a point in it, and it's got null kids. And then it's not got a point, and it's got 4 kids. So there's kind of 3 states to each of our things, and maybe we could represent the state a little bit better than this. But you started on the tree and then switched to step 2 because the tree is hurting your brain. The next thing was starting the map and the actual tree. Okay. So, yeah, all right. So let's see if this does it. So if we start off, we've got 4 null kids, and we're not a leaf. You insert into the root. Leaf is now true. It's got a point. Returns. The next time through, it doesn't do this. It checks for dupes. If it's a dupe, it doesn't do anything. Then it says, okay, I'm not a leaf anymore. It news the kids, and now the next time through, it's not going to do that one because the children have been initialized as well. And so the next time through, let's see, it'll skip that too. And so it will simply pass whatever point is on to one of the 4 kids. Then it'll recursively call. So that should work. Let's see if that works. Okay. I think there is still probably an off by 1 error in here. Yeah. So there's still an off by 1 error in here. Because when you subdivide and subdivide and subdivide, you end up getting a division of 0, and that turns into an infinite loop. So we still have that problem as well. Okay, but is it finding the points? I think it was. So true, false, false. So it found first, third, and sixth. First, third, and sixth. Yeah, that's correct. Okay, so our search works, our insert works, except when we fall into an infinite loop. All right, so let's do this. So when we create a new point, we are taking the mid, the max, and averaging them. All right. So if we have 10 and 20, it becomes 15. And if we have 10 and 11, it becomes 10. So the midpoint and the min are the same. And yeah, so we have to make sure that we handle that properly. Did we say this is inclusive? I think it's inclusive, right? So it goes from like, so if we divide up 10 and 13, it'll go 10 to 11 inclusive, and then maybe we need to add 1 to that, right? These are inclusive, right? So it's less than that, and that, and that, and that. Yeah. So we have some overlap here, I think. So we need to go maybe +1 or something, because the midpoint is going to be included on both halves. So why don't we just actually just see out the midpoints and then do it that way. So this will be probably a good exercise on how to debug stuff. Right, min, max. Let's just see what kind of numbers we're getting here. Girlfriend not found. All right. There we go. All right. So we start off making a new tree. Min is 0, 0. Mid is 50, 50. Max is 100, 100. And then we make a new tree that goes from 0 to 25 to 50, and then 25 to 37, 50. Okay. And then we end up falling into a loop here. So go from min of 29, mid of 30, max of 31, and then we go min of 30, mid of 30, max of 31, and then we divide it up again. It's the same problem every time, right? You see that? So, so this one worked just fine. Now for this one, we insert 3131 into the 2531. See, it's going to be half of this one, I think, right? Or no, it's going to be in this one. So it's going to be inserting into this tree here. And so it creates 4 kids, and then it's going to recurse into that tree between 28 and 31. Creates 4 kids, recurses into here, and creates 4 kids. Okay. So it's never finished, right? So what we need to do is go so we have min of 30, min of 30, mid of 30, max of 31. So it creates a child like this. So the child is going to be 30, 30 is the min and the and the min and the mid, and then the max is at 31, 31. Right? So so it's going to go from 30 to 30, 30 to 30, so it's a single point essentially. Right? And then, yeah, I think, yeah, okay. And then this is going to go from 30 to 30 as well, right? 30, 30 to 30, 30. So these two subtrees are actually the same, right? You see what the problem is? Like, min is 30, 30, mid is 30, 30. So this is going to be 30, 30 to 30, 30. This one is going to be 30, 30 to 30, 30. This one's going to be 30, 30 to 31, 31. And this is going to be 30, 30 to 30, 30. So you have 3 kids that are the exact same tree. And that's not good, right? So I think what we need to do is have 2 midpoints. Mid 1 and mid 2. In other words, the left side and the right side of mid. And so mid 1 will be that, and mid 2 will be 1 to the right. You guys see what I'm doing here? So like, the trouble is I'm using an inclusive where the boundaries are included in it rather than using a half open range pattern or something like that. So that's why we're getting these problems. So what I'm doing instead is I'm going to have 1 midline, which would be at like halfway rounded down, and then there's going to be another midline that's going to be half rounded up. There's going to be 1 mid y that's rounded down, 1 mid y rounded up. And so this way, when we take these points here, there's not going to be any overlap between the different trees. Yep. And I think if the size of the tree is 1, we shouldn't divide anymore anyway. But I think this will handle it. Okay. Does that make sense? Because right now the subtrees are overlapped. Like I said, there was an off by 1 error in it when we were doing it last week. And so what we're going to do is we're going to round down and round up, and now the sub-quadrants are not going to have any overlap in them because we're going to be using min 1 is the lower one, and min 2 is the upper one, or whatever, right? Or mid 1 and mid 2. Okay. Mid 1 and mid 2. So rounding down, rounding up, and then this should stop the overlap problem. So now we need to pull up the cheat sheet that we made last time. And the first quadrant is going to be, this is min down here, right? It's min, and it's going to go up to mid 1, right here. And then this point here is mid 2, and that point here is max. So the lower left and the upper right are pretty easy. It just goes from min to mid 1 and mid 1 to max. So lower left is min to mid 1, min to mid 1, and the upper right is going to be mid 2 to max. Those are the easy ones, and then upper left is going to be this point here is mid 2 dot y as the row, and the column is going to be min dot x. So min dot x and mid 2 dot y, and it's going to go up to mid 1, that's left side, dot x, and max dot y. It always helps to sketch these things out. There's no point trying to figure them out. Do you guys see what I'm saying here? Like this point here, that row is mid 2 dot y. I don't know if you can read my handwriting. This is mid 2 dot y. That's the row we're on. Okay. Change inside so it's inclusive to the bottom left and exclusive in the top right. Yeah, you could do it that way, right? That would definitely work. And then we also need to make it so that we don't insert into four kids at the same time. That's the other problem. Is that, you know, the insert code that I have here assumes that it will only be inside of one of them, and it's going to be recursively calling into 4 of them and splitting 4 of them down, which is bad. But hopefully fixing this will solve that, so they won't be overlapping at all. Okay, so the lower left point is min x, min dot x, mid 2 dot y. X, and this is mid 2 dot y. Upper right corner is mid 1x, max y. Okay. And then for the lower right, we've got this point here, which is, that's min y, and it is mid 2 dot x, to this point here, which is maximum x, and mid 1y. Mid 2x, mid y. And max x, mid 1y. Okay. And then just for safety's sake, I'm going to turn all these into else ifs, even though it shouldn't come up anymore. So we'll just make a note if it failed to insert also. It's probably a good thing to catch for it. Die does not exist. But we can fix that. Void die. S equals bad input. Scare. S. Okay. So no more infinite loop. Yay. That's what I was trying to convey to you guys last week without kind of giving it away. That when you subdivide, you have to be really careful. And this happens a lot in computer science. If you're doing like a binary search, and like you have 10 elements, and you know they're sorted, and you're trying to find an element in it, you start halfway, and then you jump halfway to the left or halfway to the right. You have to be very careful with those off by 1 errors, right? Because like, you know, 5 divided by 2 is 2, right? And so starting at 5 is fine. But then you go 2 to the left and you go 1 to the right, or 2 to the left and 1 to the left, and then you actually can't get to 0, right? And so you have to be very cautious when, whenever you're doing repeated division like that, you're handling the off by 1 errors. You're handling division with odd numbers properly, and this is a great example of that in computer science. So yeah, I like your solution also, just not make it overlapping like it was. But I kind of wanted to leave it as a little bit of a challenge for you guys, because this wasn't a lot of code, but it was enough to like be kind of a fun debugging assignment. And let's see here. Let's see if it's working. True, false, false, false. True, true. Let's see here. True, false, false, false. True, true. Okay. There we go. So there is Quadtree. Now, did you get it working with mouse clicks and things like that? So basically, we need to do rendering, right? So that was hopefully a quick fix, even though it looks like it wasn't. Storing the map in the actual tree, right? So making the map editor. So does your code work, Corrente? Take a look at it. Except for the access grant. That's Quadtree map maker. Okay. All right. Ooh, I like that. I'm gonna go with Kirokaze. All right. Let's build the map. Nice. Oh, but it's not leaving the green behind. What's happening here?
I didn't turn the cursor off, but select the color. Click a number.
Oh, okay. So,
it doesn't save because I didn't do that yet. I was doing this this morning, but that's what I got to work.
Gotcha. Yeah. Basically, I think there's actually a way of doing mouse drags in Putty as well. And it's resetting the whole screen every time you change the palette, huh?
Yeah.
Yeah, I do like the notion of having a palette. All right. So yeah. So the goal is, I don't think my colors library supports mouse drag support. I could probably add it if you gave me an hour or so. But yeah, I like it. It's a good start. You need to turn off the cursor too. That's a little distracting. And so you can do that if you go into colors lib cursor. I think it's called show cursor or something like that. Move cursor, show cursor. Yeah, so just call show cursor false, and then that'll turn the cursor off and it won't be distracting to you. And yeah, these are all escape codes that are not very well documented anywhere. And so, in order to make this library, I had to go through like a 1970s and 80s era documentation and try and find that out. You got the callbacks working, so that's cool. Why don't I look into doing drag support, and then Stover, do you want to fix the Quadtree in your code and then start working on the map editor? And Corrente, why don't you work on it right now? I'm going to stop the recording because that was kind of like, all I really wanted to show was how to fix that bug. See if there's anything else in here that we need to actually look at. Search works. Oh yeah, raycasting, right? Right. And so raycasting, basically you're gonna pass in an array, right, which is a point and a direction and a length. And there's actually multiple ways of doing rays, but let's talk about that a little bit, I guess. So let's say you've got your Quadtree all kind of set up, right? You got your stuff in it, and you want to shoot a ray through the world, right? So there's 3 parts to a ray. There's the origin, there is the direction, and then there is the length, and that is it can be infinite if it doesn't hit anything. If it hits something, then it'd be t is the length of it. T is the time. that's one way of holding array. Another way is you can just hold it as a pair of points, right? So you can have point 1, point 2, and that's a line segment. And you can shoot from point 1 to point 2, and then t would be the fraction, like 0.7, that it got to before it hit the point. And so that's, you know, just they're both mathematically equivalent. The only trouble with doing a line segment like this is handling vertical lines, because the slope is infinite, right? So you have to kind of handle that. But yeah, in general, like you'll see a lot of code that uses 2 points, and you know, find out what it hits between here. And right now we're only doing Quadtrees with points, just to make life easier, because if you put in like a circle or something, the circle could span both axes of the Quadtree, and then it would have to subdivide, and you know, and so this subtree would be pointing to it, and that subtree would be pointing to it, and or what commonly happens, you slice it in half, and now you have to deal with semicircles, and then you slice it again, and it doesn't cut it evenly. That was terrible. That doesn't line up right at all. And now you've got quarter circles. And so sometimes when you've got objects that span boundaries, you can either have both sides kind of adding it to their list. And so when you do array intersection tests like this, you would test to see if it hits the circle, because the circle is inside of the Quadtree. And you don't have to subdivide once you get past 1. I mean, we did it for our assignment because we're just doing points, and so you click again, and it's like, all right, that's fine, just add that there, and you click again, it's like, all right, subdivision time, you know, and you click again, all right, subdivision time. But that ends up creating a lot of Quadtrees, right? You know, especially if you've got 2 points like right next to each other. Oops, you can actually draw a line between them. If you've got 2 points like right next to each other, then the Quadtree will subdivide, and it will subdivide, and it will subdivide, and it'll subdivide until it splits those guys in half. And so there's a couple different solutions to that. Yeah, one is without even abandoning Quadtrees. So you just allow, you know, 5 points in a Quadtree bucket before you subdivide, and that, you know, makes life simple, right? Instead of having a point, you have a vector of points, and then anytime you array cast, you just check at most 5 people in that bucket and move on, right? You're still not checking all the people in the world. You're checking at most 5. It's not too bad, and that kind of keeps you from having to, like, especially when you have 2 things like really close to each other, you end up making a lot of subdivisions just to get to the one point where you split it. Do you guys understand? That makes sense? So you can sometimes have like a list of objects, and you split when the size is like over n, right? So and that'll cut down on the depth, because you know also when you do this kind of stuff, you're going to be traversing the tree a lot, and if your tree gets really deep, then your runtime performance drops down. And so having the ability to have like 5 points or whatever, it's a tunable parameter in a bucket, then that prevents you from recursing down too deep. All right, so that's one approach. And so this is a quadrametry, and the maybe better version of a quadtree is called a KD tree, named after the inventor KD. No, a KD tree doesn't divide necessarily along the halfway point like we did. Okay, so a KD tree, say we do this, and we do this, and we put a point here. Okay, that's fine. Let's say we've got the same restriction of no more than 1 point per quadrant or whatever. And we do 1 here. Okay, that's fine. And now let's say we put a point right next to it. Now with a quad tree, you're going to subdivide and subdivide and subdivide, because you go in half every time, right? And with a KD tree, what you do instead is you pick the splitting plane. So you pick like that plane right there, right? And you draw a line right there. And so the left, that's the left child, that's the right child. Does that make sense? So you, rather than your midpoint being just halfway between min and max, your midpoint is chosen intelligently. And that's the only difference. That makes sense? And the next time you got a point, then you pick a splitting plane that will split the 2 points, right? Because you know what your 2 points are, right? So split it. Pick the splitting plane halfway between it, right? And if we put another point here, we can split it here. That makes sense? What do you guys think? Yeah, because if you have a bucket of things, and what you do is you find a splitting plane that'll split the, like if you have 5 points and you're adding a sixth one, you find a splitting plane that'll put 3 on one side and 3 on the other, whatever. Yeah, it's a little bit more work because you have to kind of like, like let's say we got a point here. Let's say this point here is at 100, 100. I'm just picking numbers, and we insert a new point up here, which is going to be at 108 and 150 or whatever. So we're doing a vertical split here, right? And so the vertical split will go at, let's say, 108 plus 100 divided by 2, 104. So at 104, we draw the splitting plane. And then we put a point here at, so I should put it back down here at 100 so I have an even number. And then it'll average 150 and 100 and get 125 and split it here, right? See, so as long as you have 2 points, you just average the x or the y coordinate, whether you're doing a horizontal split or a vertical split at the time, and just put the thing right down the middle, and there you go, KD tree. So the Bridges people have a pretty cool KD tree. KD tree Bridges. And you alternate between horizontal and vertical, yeah. So you split, split vertically, split horizontally, split vertically, split horizontally as you recurse down the tree. And you find a splitting plane that just will give you a good split. Okay. And so here we have a KD tree by the wonderful people at UNCC. And the C++ code, KD tree elements. So there's, I think they just made all these manually, and then they're just going to link them up. So they're not doing the splitting here, and they free them up there. They visualize it. Okay, so that's going to visualize as that is not the one I'm thinking of. Yeah, but you see each one's still a rectangle, right? And it's still an axis-aligned bounding. It's an axis-aligned rectangle, right? It can't rotate, things like that. It's just x-axis, y-axis, right? And then the splitting planes are, you hold the splitting plane in there as well. So let's see if I can find their Mickey Mouse one. No, I guess not. This is definitely not the kitty. No, this is not what I'm looking for. Car break-ins at Charlotte, no. Magician's House, The Bridge in the Clouds. Bill's Thrifty Rooter, that is not me, and I do not live in Yuba City. Huh. Well, what they did was they took an image of Mickey Mouse and they split it using a KD tree. And so basically, the assignment, which I might have on my computer actually. Do you have any questions about it while I'm looking this up? Yeah. Yeah, this is the... No, this is not what I'm looking for. This is the Bridges code, but not what I'm looking for. No. Yeah, I'll have to find it. But basically, yeah, the intelligence in a KD tree comes from like figuring out where the splitting plane should go. Now, the next level beyond a KD tree is called a BSP, and in the same way that you know how we talked about earlier in the semester that you can have AABBs. Do you guys remember what an AABB stands for? Stover, Krente? You don't? It's an axis-aligned bounding box. So, so let's say that you've got a spaceship or something like this, and you want to see if it's going to run into something, right? It's actually kind of annoying to see if like something like runs into something. You can do precise calculations using convex hulls, which we've talked about before, right? You guys remember convex hulls? Convex hull is a concave polygon. If I draw it properly, it's a concave polygon. And you can test to see if any point is inside of a convex hull by just doing a cross product with all the each of these vectors. And so if it's to the right of all these things, if you trace a loop to the left, or clockwise rather, if it's to the right of all of them, then that point's inside. And so you can do intersection testing and things like that with it. Basically, if any of the points of one polygon are inside of another one, then they should intersect. I think. I'd have to think about that a little more. Anyhow, it's expensive, right? And so rather than doing a convex hull, usually what we do is we wrap what's called a bounding box around a complex object, right? And so a bounding box makes collision tests easy. If you've ever played a video game where like you shoot this area on a person and it hits them, that's because they have like a cylinder probably for the person. So like there's like a circle up here and it just goes down, and so that area there and that area there is shootable on a person if they have really cheap collision detection. So that's a bounding box is a box you just wrap around an object. So you got your spaceship there. The spaceship is just wrapped in an axis-aligned bounding box. Axis-aligned means that this is the y-axis and this is aligned with the x-axis, right? And so it doesn't rotate at all. So as the spaceship rotates, you actually oftentimes have to resize your box because things at an angle are going to be bigger than things that are horizontal or vertical, right? And so this axis-aligned bounding box will change as the spaceship rotates around. Or what you do is you just figure out the maximum distance away, and you just make your axis-aligned bounding box a little bit bigger, then the thing can rotate within it freely, which is a cheap trick that you can do if you don't want to update it every frame as the thing's rotating around. So intersections between bounding boxes is very easy, right? There's what's called the splitting plane algorithm, which is to say if you can find a spot on either the x or the y-axis that can split the two of them, that is in between the two of them, then they do not touch, right? And so if you have these two rectangles here, you can find this splitting plane here. If you can find a splitting plane, they don't touch. And so what you do is you just look at the max x and the min x, right? You look at the max x for this one, the min x for this one. Like the min is bigger than the max, therefore they don't touch. You do the same for the y's, and you do the same for the other side. So it's 4 tests, very simple if statements, and then you can see if they intersect or not. Bounding box intersections are trivially easy, right? And then you also have what are called bounding spheres, right? Bounding sphere is also very common, and a bounding cylinder, like they use for people, is a bounding sphere extruded as a box downwards. So it's both a bounding box and a bounding sphere. It's a bounding sphere in the x, y directions, it's a bounding box in the z direction. So if we had a convex hull and we wrapped it in a sphere, you find the midpoint and you just wrap a sphere around the whole thing. And now the thing is free, if I drew my circle properly, the polygon is now free to rotate to its heart's content, right? And it doesn't matter, you don't have to update the sphere, because what you do is you find the furthest point on the polygon that's away from the centroid, the center mass of it, and then you just spin that in a circle, and that is your, in this case it's a bounding circle, but in 3D it's a bounding sphere, right? And then in order to do a collision test with another bounding sphere, you take the distance between the two centroids, the two center points, center points of mass, like that. Do you know how to tell the distance between 2 points? In C++, the function starts with high. Do you remember how to tell the distance between 2 points using the powers of algebra? High pot. That's exactly right. So if this guy has a radius of 1 and this guy has a radius of 2, it's not very visible, whatever, and the distance between them is 5, they do not touch, right? Because one of them sticks 1 meter in this direction, one of them sticks 2 meters in this direction, but their center points are 5 away, they don't touch. And so it's a really easy test. You just compute the hypot, the Pythagorean distance between 2 points, and see if the sum of the radii is greater or smaller than the distance they are away. All right, if the distance away is smaller than the sum, they touch, because it doesn't matter which way they're oriented, they're a sphere, they're going to hit. And if the distance between them is bigger than 1 plus 2, then they don't touch. And if they touch exactly, then you have to decide, again, are you going to use inclusive or exclusive comparisons, and just be careful with it. Right. Does that make sense? Bounding sphere, bounding box. Axis aligned bounding box. So axis aligned bounding boxes are always not rotated. They're always on the x-axis and the y-axis. Okay. Now, let's talk about OBBs. An oriented bounding box. So an oriented bounding box is nice in one sense, like you got your rocket. You got your rocket, and an oriented bounding box is a rectangle that can rotate. It doesn't have to be aligned to the x and the y direction. The exhaust is not part of the spaceship. There you go. And I'm going to color it in galaxy colors. There you go. There's our spaceship. Okay, and then the cool thing about this is that as the thing rotates around, and let's see, do I have a rotation box here? No. Why do I not have a rotate? There's usually a rotate handle on these things. Oh, whatever. As this thing rotates around, the OBB rotates with it, right? And so you don't have to constantly be recomputing your boxes. It'll just slide with and rotate with the thing no matter which direction it goes in. And so if the thing is pointed this way, then the OBB rotates this way. If it's pointed this way, then the OBB is pointed that way. And so it just kind of goes with the model. It's kind of nice. The trouble is like doing an intersection test between two OBBs involves a little bit more work. You have to basically rotate one of them so that it is an axis line bounding box, and then you can still do the dividing plane algorithm to see if they intersect or not. So now the data structure equivalent of this is called a BSP. And so the Bridges guy actually was a grad student under the guy who invented BSP, which is the file format, and did I say BST? No. Surprise. BSP. Okay. And so BSP is the oriented bound. What is that? Is it OBB or is it OOBB? Yeah, it's just OBB. It's not object-oriented bounding box. I've been doing a lot of OOP recently, so OneNote is glitching again. Let me close it out. So the so the KD tree, right? Do you guys understand how the KD tree works? You insert a point, and you insert another point, and it picks a dividing plane, right? You insert another point, and it picks a dividing plane. But they're all axis aligned. So the equivalent of the OBB, the oriented bounding box in data structures, is the BSP, the binary space partition. So a KD tree is kind of the philosophical equivalent of an AABB, and the BSP is like the philosophical equivalent of an OBB. And so what does that mean? That means that you can pick any direction for the dividing plane that you want. Okay? So let's say that we're doing our thing just with points again. And this is the x direction, this is the y direction. I don't know. They're not really splitting planes, but I just want to have something there for reference. So you start off, put a thing here, and then you put a thing like here. Now, if we were doing a KD tree, we would probably do that, right? We would just do a vertical line like that. With a BSP, you can actually split it using any orientation of planes that you want. And so if you have a thing over here, then the child could split it this way. And then you have one here, you can split it this way, right? And this can actually end up forming a closed, area, right? And so what you can actually do is just say this whole area here. Are you glitching already? I just relaunched you. See, it's accepting the touches, but it's not actually selecting the pen. It is such a weird, glitchy program. Okay, all right. There we go. All right, cool. And so you can basically use a BSP to define regions of space. And you can actually say this whole region of space here is solid. Okay. And you can have a dividing line going this way. And you can say this whole area here is lava. That makes sense? And so it's a binary tree. You can have a KD tree as a form of BSP. And then you can do all sorts of cool things, like say, all right, if my camera is here, and I'm looking this way, then draw this thing. This thing's going to be in front of this thing, right? So draw that first, and then any areas that are not occluded by this box here, draw this behind it, things like that. Does that make sense? Stover, Corrente? So rather than all of your splitting planes always being on the x-axis or the y-axis, you get to pick your splitting plane. And you can do that so you have less depth to your tree. Because like you saw with the quad tree thing, if you have two things that are very close to each other, you'll end up splitting till you get to the point where you've got the 1 unit wide tree there. And it has a very deep tree depth. With KD trees, you can do a little better by just never splitting more than once every time you add a new point. You only have to add one more split. But with a BSP, you can actually split, like especially if you have a lot of points to begin with, or a lot of objects to begin with, you can choose your splits very intelligently and create a tree that is not too deep. And it takes a while. Like constructing an optimal BSP tree is actually I think it's an order 2 to the n algorithm, if I recall correctly. Like to find the absolute best way of splitting up. You got all these boxes and objects in the world, and if you want to find the optimal way of building a tree, where it says, all right, here's the dividing plane, half the objects are on this side, half the objects are on this side, here's a plane, half are on this side, half are on this side. I believe it's an NP-complete algorithm. But there's a lot of heuristics that people use that do good enough in a reasonable amount of time. So let's see what we got here. Interactive demo, oh, that's cool. That's neat. All right. Map size. It's segfault. Okay. So one division. Okay. Then it randomly. Oh, it's like a KD tree, really. Yeah, this isn't really a B. I mean, it is technically a BSP, but this is a KD tree. You see this? So it's picking a random splitting plane, and then in the splitting plane, inside of it, it is connecting sort of arbitrarily to the neighboring nodes. That's kind of cool. Huh. Cool. I like it. So that's really a KD tree. So he discards any container with a vertical ratio that is too elongated. I mean, technically KD trees are BSPs, but really it's really not what I'd call a BSP. So, yeah. So what they typically do in 3D is you have all these objects, and they'll use the plane, the surface of one of the objects, as a potential splitting plane. And then they might just go through every polygon in the world and figure out which splitting plane will put half on one side, half on the other side. Now the trouble is, yeah, I just need to think of how to implement and code it. Yeah, it's harder, right? Like Quadtrees are the easiest, and you already hurt your brain on that one, right? Quadtrees you just always divide halfway, right? With KD trees you have to figure out a split, and with BSPs you have to figure out you can have any angle, right, that you want to split, and that's a much harder problem than just dividing by 2. So who's my there it is. So if you have a like you have a couple objects in the world like this, and you want to create a binary space partition on it, typically the algorithms, and like I said, you can kind of do any place as a splitting plane arbitrarily, but usually they'll do something like this. Like they'll look at, maybe we'll do that, and if you do that, it's actually going to cut the object in half, right? So not exactly half, but it's going to cut it into 2 pieces, right? And so then you've got to glue them back together and make sure there's no seams on it when you render it later. So that's a potential splitting plane. There's a potential splitting plane this way. There's a potential splitting plane this way that will cut the triangle in half. There's a potential splitting plane this way that'll chop that rectangle in half. Right, and so if we could do this one, but then everybody's on one side, we could do this one, but everyone's on one side, and so basically you could just go through every face in the world, which is not a great thing, and you can read papers on how to do this better, but it might give you an idea of kind of a starting point to think about it. So you can just look at every edge in the world and kind of figure out, okay, well maybe this one here is the best, right? Because if we use this as our starting splitting plane, then we've got one object on one side, 2 objects on the other side. That's pretty good. It's within 1 of each other. No splits are necessary. Yeah, that's pretty good. Okay, and then for the left half, we only have 1 object, so we're done. And then for the right half, we could go through all the different edges on here, and maybe we pick this one, or maybe we pick this one. Either way, we'll have 1 object on one side and 1 object on the other side. Maybe we'll pick this one here. And then the right child is that side, the left child is that side. Okay. And then if you want the BSP to like fully encase the thing, you can put another thing in here and mark this as solid, right? Like if you want to have your BSP like fully describe the thing, like you could subdivide and then mark the leaf nodes as solid, and then that is actually what they used for the file format of Doom 2 and Quake, for that matter. Quake is a 3D BSP. Doom 2 is a weird 2.5D BSP, but you can just tag the leaves as solid if you want. And then if you want to do a point contents test, like if you want to say, hey, what is here? Well, you start at the root, go to the right, go to the left, go to the right, go to the left. Okay, it's tagged as empty, nothing there. Go to the right, go to the left, go to the left. What's here? Oh, it's solid. There you go. If you want to do a trace line, you can, do that. See what you hit. So when you render it, the camera is somewhere in the world, and which of the leaves are nearer to you than others. You draw those first. Later on, it's not even used in because the GPU will just kind of do a lot of that stuff for you, but it's useful for occluding things and stuff like that as well. Okay. So, yep. And there's a lot of research on these things. Yeah, it's 89, 92, things like that. So dynamic changes to BSP trees, that kind of stuff. All right, so that is that. So I'll give you guys another week to do the quad tree thing. I want you to make a good map editor. Next Tuesday, yeah, let's have it done by start a class on next Tuesday, because we're actually going to use this in CSI 45. So I'm going to give you guys an extra week, but it really needs to be done by then, because we're going to be using it. This is going to be the map editor for our next CSI 45 assignment. So your code is going to be the front end to maybe the final coding assignment in CSI 45. So it's all on you, Corrente. Make sure it works. And I will I'll see if I can get dragging to work so that you can actually just drag a line at once rather than having to click on it a bunch of times. Okay? I'll check in with you guys in about half an hour. All right. So what did we cover today? We went over Quadtrees, KD trees, BSP trees, and related concepts, starting with a highly interactive and engaging debugging session on the Quadtree thing. All right. Peace out, you guys. Bye.